All right, so welcome to Recitation 2 for the second week, which I guess makes it our fourth recitation altogether. So today I wanted to talk about distances. We've talked about distances in a few different contexts, and it can get pretty confusing. And some problems reduce to other problems, and so on and so forth. So I just have a bunch of examples of problems involving distances that we could take a look at. And so here's an overall summary of a lot of the problems I want to think about today. So the first one we talked about on the very first day of class, the distance between 2 points. That's something that I'm not going to go over today, but remember you just subtract the corresponding coordinates and square those and add those up and take the square root, and that's that. And so actually all these other with the exception of one, I think it shows up a little bit. For the most part, we won't actually be using that distance formula for any of these other distance questions. So the other types of distances we're talking about are between a point and a plane, between a point and a line, between parallel planes, between parallel lines, between skew lines. And then I just want to go over a couple other distance questions that aren't fitting into any of these categories, but yeah, let's take a look. So distance between the point 1, -2, 4, and the plane 3x plus 2y plus, ooh, that should be a z. Sorry about that. I'll fix that. Let me write that down so I don't forget. So, maybe I won't because I don't usually post these blank ones. I will just fix this here. That is a z. Okay, and so there's a couple ways you could do this. I like the scalar projection method because it really emphasizes what's going on with that. But there is a formula in the book that you can use as well. So I'll show you both ways here just so you can choose what you like better. But my way that really emphasizes some of the geometry of what's going on here would be to imagine the following picture. We have our point 1, -2, 4. And we want to figure out how far it is from the plane 3x plus 2y plus 6z equals 5. And so the way we could do that is we could pick any point, and let's call this point P. So let me fix this a little bit. That's point P. I'm going to pick point Q, which is any point on this plane. And so we just look at the equation and we pick any point that we want. I hate fractions. And so, for example, you could use 5/3, 0, 0, for example. That works, right? Because 3 times 5/3 plus 0 is going to be 5. You could do, 0, 5/2, 0. But I don't want to deal with any fractions. So I'm just going to pick 1, 1, 0, right? Because that works. 3 times 1 plus 2 times 1 plus 6 times 0. Most days of the week is equal to 5. So anyway, 1, 1, 0 is indeed on that plane. And so what are we going to do now? We're going to get the displacement vector QP, which is going to be the vector what? 0, -3, 4. Just do coordinates of P minus coordinates of Q. We get, 0, -3, 4. And so then what we're going to do is we're going to project that onto the normal vector of this plane. So this normal vector is 3, 2, 6, right? That's the coefficients of x, y, and z on the plane equation. And so remember, the whole point of the normal vector of the plane is that it's perpendicular to the plane. And so then this green distance here is the absolute value of the scalar projection onto, I guess I'll call this n, right, the normal vector of the plane, scalar projection onto n of QP. So scalar projection is basically the length of the vector projection, but the scalar projection can be negative if the vectors make an obtuse angle. And so yeah, if this ends up being positive, then that is the distance, but in case this picture is actually flipped and they make an obtuse angle with each other, we'll just take the absolute value to make sure that we get a positive answer for this distance. And so anyway, the formula for scalar projection is, remember, the dot product, so n dotted with qp over the length of the vector that we're projecting onto, which is, in this case, n. So we're taking the absolute value of n dot qp all over length of n. Okay, and so we get the absolute value of 3, 2, 6, dotted with 0, negative 3, 4, all over the length of 3, 2, 6. And so what do we get? 0 minus 6 plus 4 times 6 is, so what? Negative 6 plus 24 is 18. And then the length of 3, 2, 6 is what? 9 plus 4 is 14. Plus 36 is 50. So 18 over the square root of 50 looks like our answer. I did not do that right. It's the square root of 49, which is 7. Yeah. 9 plus 4 is 13, plus 36 is 49. Okay, and so that's our distance. The other way you could do this is, in the book, there's that formula, if you care to memorize it, that the distance from x1, y1, z1 to ax plus by plus cz plus d equals 0 is the absolute value of ax1 plus by1 plus cz1 plus d all over the square root of a squared plus b squared plus c squared. So this formula is derived from drawing this picture and just doing it all in terms of a, b, c, x1, y1, z1, but it's the exact same idea, but I found in the past that students like having a formula that they can use. And so yeah, if you want to do that, then I guess it would be the distance from, or whatever, I could just write it like this. In red, our point was what? 1, negative 2, 4. And then our plane is going to be 3x plus 2y plus 6z. And then be careful, if you're using this formula, you have to write it in that form. So I have to rearrange this to minus 5 equals 0 to get the, yeah, in fact, d is minus 5. So you got to be careful with that. That's one reason why I don't like this formula. If you miss that one little detail, you get the whole thing completely wrong, whereas if you understand the geometry of what's going on, that's a little bit safer. So anyway, let's plug that in and make sure we get the same thing. So that'll be what? Absolute value of 1 times 3 minus 2. Well, I'll write it the proper way. Technically, a is 3 plus 2 times negative 2 plus 6 times 4 minus 5 all over the square root of, we already did this before, but 9 plus 4 plus 36. So what? 3 minus 4 is negative 1, plus 24 is 23, minus 5 is 18. And yes, of course, we get the same answer. So it's your choice. Distance point to plane, you can either draw this picture, which I think the picture, that technique will serve you well in the long run. But if you prefer to memorize this and not screw up any of the little details with the with regards to the sign of D, then that's up to you as well. All right, so that's distance between a point and a plane. Let's do distance of a point to a line. And so we actually put this on the homework from last week, the first homework assignment, because this idea, for the most part, comes from the cross product section. So it's a little bit different from the other ones that we're about to talk about today. So anyway, the picture you want to have in mind for this situation is, okay, we have our point 1, 1, 1, And then we have our line whose equation is r of t equals negative t, 6 minus 2t, 8 minus t. And we want this distance. So what we can do, and I don't know, we could call this P. We could pick points Q and R on our line. So for example, we could pick our two favorite values of t, which are probably 0 and 1, to get that point Q. If we plug in t equals 0 to the line, we see that the point 0, 6, 8 is on our line. And then if we plug in t equals 1, I get that the point negative 1, 4, 7 is also on this line. And so I guess I now want to imagine a triangle. So that's what the hint I gave up here in our little summary was that distance between point and line, think triangle area. So what is the triangle area gonna be? Well, so the area of PQR is, well, maybe I'll write it over here. Sorry, area PQR is 1/2 base height. Well, what is the base? The base is going to be the length of vector QR. And then the height is precisely what we're looking for. That the height is the distance from P to the line, right? Because that's one of the facts about basic geometry, is that the distance from, the shortest distance from a point to a line is going to be when you go in perpendicularly like that. That this point on the line is farther, this one's farther, this one's farther, this one's farther. This point right here is the closest on the line to our starting point. And so that when we say find the distance between two objects, we're asking for the minimum, the closest thing on those objects. Okay, and so, yeah, let's just call that D. That's what we want, the distance that we're trying to solve for. So I'll just call that, I'll make that red just so we can keep in mind that that's what we want. Okay, and then the other hint I gave was think triangle area and length of cross product. So we also know that this is equal to 1/2 the length of P. Well, just, it doesn't matter what we do. We talked about this a little bit before. I guess this was on Wednesday's recitation. I showed you that, well, I guess this was more about something that Dom talked about last week, but you know, I mentioned on Wednesday's recitation that often there's different choices you can make. As long as you're making a correct choice, you'll get the correct answer, so that's fine. And so anyway, it looks like we could solve and get that the distance that we want is going to be the length of QR cross QP over the length of QR. And so, like I said, we put this on the homework last week, so hopefully this is a little bit familiar, but I guess let's figure out everything. QR is what? -1, -2, -1. Yep. QP is what? 1, -5, -7. This cross product QR cross QP is what? 14 minus 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 5, so 9. And then -1 minus 7 is -8. And then 5 minus -2 is 7. Okay, and then I guess QR, okay, so then that's the length of 9 minus 8, 7 over the length of -1, -2, -1. So I get what, 81 plus 64 plus 49 over square root of 6. So whatever that ends up being, some number. Okay, so that's the hint for point to line. Is get 2 points on your line using any two t values that you want, and then set up the area of that triangle, and that should get you to what you need. All right. Distance between planes. So with planes, there's two possibilities. Remember, planes can either intersect, in which case they look something like this, whatever, or they're parallel. So if they intersect, then the distance between them is 0, right? Because there's points that they have in common. There's no separation between planes that intersect. But if we have parallel planes, which is what we have here, then there will be a distance. And so notice that these are in fact parallel planes because the normal vectors are parallel vectors. So n1 is 2, negative 3, 1. n2 is 4, negative 6, 2. So notice that 2 times n1 is n2. So those are in fact parallel planes. And so the distance we're after is this distance here, and it's the same, right? That's the whole situation with parallel planes, is that that separation remains constant. And so actually what you could do is say that this distance is the distance between any point on the first plane and the second plane. That, I guess at that stage, it doesn't make sense to put perpendicular symbol with the point, but just, you don't really need that entire upper plane there. So the idea is that you pick any old point on one of the planes and find the distance to the other plane. So let's call this, plane 1, plane 2. So the point on plane 1, we can use, for example, 2, 0, 0, right? 2 times 2, and then 0, 0, that's going to give us 4. So 2, 0, 0 is on plane 1, and then plane 2 is, 4x minus 6y plus 2z equals 3. And so now it's a problem that we solved a couple minutes ago. We could do it again just for fun. Remember, the idea is that we have our normal vector n, which in this case is 4, negative 6, 2. We could pick any point q on plane 2. And is there a way to do this without fractions? Is there an easy way to do this without fractions? I don't see anything. So anyway, I'll just do 0, 0, 3 halves. All right, if I set x and y both equal to 0, I get 0, 0, 3 halves is on plane 2. And so at this point, my distance that I want is the length of the scalar projection onto n of QP, which in this case is going to be what? The absolute value of 4, negative 6, 2, dot product. So QP is going to be 2, 0, negative 3 halves, and then divided by the length of n, which is the square root of what? 16 plus 36 plus 4. And Yeah, whatever that ends up being. So what? 8 minus 0 minus 3 is 5 over square root of 56. Looks good. So for parallel planes, you basically throw out all but one point on one of the planes and then treat it as distance between a point and a plane. And so that's the hint I gave up in this summary. Pick any point on one plane and then find the distance from that point to the other plane. Okay. And so then we have the same kind of thing happen for parallel lines, that the distance we're after for these parallel lines, all those distances are the same. So distance between parallel lines equals, well, same story. Pick one point on one of the lines and throw out the rest, and that's the distance we're after. So, okay, we could have this be R2 of t is what? 2t, 1 plus 4t, 2 plus 2t. And then my favorite point on the first line corresponds to t equals 0 on R1, which is going to be what? 2, 3, 3. We could call that point P. And then what we did a few slides ago was get our 2 points Q and R on this line. So point Q, I could do t equals 0 on R2 to get what? 0, 1, 2. And then R could be t equals 1, which is going to be what? 2, 5, 4. And so then we figured out before that the distance that we want is going to be the length of QR cross QP over the length of QR. Again, remember we thought about the area of triangle PQR equals 1/2 base height. Height is that red distance that we're looking for. And from there, you can keep going. So what? QR is just going to be what? 2, 4, 2. So the length of 2, 4, 2 cross what? QP is going to be 2, 2, 1. And then over the length of QR. And so this cross product 2, 4, 2 cross 2, 2, 1. I always have to do my cross products like this, is what? 0, 2, 4 minus 8 is -4. So I get the square root of 0 squared plus 2 squared plus -4 squared over the square root of 2 squared plus 4 squared plus 2 squared. And so what is that? Square root of 20 over square root of 24, which I suppose you could simplify some, is what? The square root of 5/6. But that's not so important. But yeah, there we go. Okay. So now for probably the trickiest one for today is, how do you find the distance between two lines that are skew? So remember, yeah, lines in R2, if you're in the XY plane, lines can either intersect or be parallel. But if you're in 3D, that's 3 dimensions, and each line is only 1 dimension. So you have more freedom. And so it turns out that lines in 3D can either intersect, be parallel, which means they have the exact same direction, or they could be skew, which means that they don't have the same direction, and they also don't intersect. So skew lines can't exist in the XY plane, but if you're in space, there's more room, and it is possible to have non-parallel lines that don't intersect, and that's what the definition of skew is. And so the way we could find the distance between these skew lines, it's actually going to follow from, I think, the trick to drawing them so that they actually look skew. So I've realized it's hard to draw skew lines, but one way you can sort of do that is to draw them in different parallel planes. So it turns out that there's a fact that if you have skew lines, so if, let's say, L1 and L2 are skew lines, it's possible to find parallel planes P1 and P2 such that P1 contains L1 and P2 contains L2. So here's the picture. There's L1, there's P1, there's L2, there's P2. And so yeah, the way you can imagine skew lines is, or try to draw them is, here's one line that lives in plane 1, here's another line that lives in plane 2, and then the idea would be that these 2 planes are then parallel. So you can't really see the lines anymore, but we have a line in this one, a line in that one that don't have the same directions, but that's the idea. And so this fact is a little bit tricky to convince yourself of. And if you're really curious, if you're skeptical and don't really believe it, we're going to do it in a second. And so you can just check. We're going to prove this statement by construction, that I'll come up with P1 and P2. And sorry, it looks like I have a slight little typo there with my vector slanted bracket, or brace, angled brace. I don't know what you call that. All right, so how are we going to find these planes? So the idea is that they're parallel planes. And so we'll use the same n for both P1 and P2. So yeah, that's what it means for planes to be parallel, is they have parallel normal vectors. We'll just give them the same normal vector, right? Parallel means you can scalar multiple, so stretch it or flip the direction, but we'll just use the same exact n for both. And so what you could see here is that n is perpendicular to plane 2. So it's perpendicular to every direction on plane 2. But if L2 lives on plane 2, then V2 has to be perpendicular to N. And same deal up here, that if L1 lives on plane 1, then whatever direction L1 has, let's call that V1, has to be perpendicular to N. So, okay, we want N to be perpendicular to V1, which, V1 is, oh, I should have put a 1 here. Sorry about that. 1, 6, 2. Remember the direction of a line, you look at the coefficients of t, so 1, 6, 2. And then we also want n to be perpendicular to v2. And v2 is what? 2, 15, 6. Okay. And so now you go back, okay, to last week. What do we do when we want to find a third vector perpendicular to two given vectors? Well, we take the cross product. So I'm going to do 1, 6, 2 cross 2, 15, 6 to get what? 36 minus 30 is 6. Then what? 4 minus 6 is negative 2. And then 15 minus 12 is 3. Okay. So that's the n that I'm going to use for both. And then now I could just pick any point on L1 and L2 to use for my plane. So L1 t equals 0 gives the point, what, 1, 1, 0. L2 t equals 0 gives the point, what, 1, 5, negative 2. And so plane 1 has equation 6 times x minus 1 minus 2 times y minus 1 plus 3 times z minus 0 equals 0. And plane 2 has equation 6 times x minus 1 minus 2 times y minus 5 plus 3 times z plus 2 equals 0. And so you could then simplify it to plane 1 is 6x minus 2y plus 3z equals what? 6. Oh yeah, so negative 6 plus 2 is negative 4. If I move that to the other side, I get 4. And then plane 2 is going to be 6x minus 2y plus 3z equals what? So negative 6 plus 10 is 4, plus 6 is 10, so when I move that over, that's going to be minus 10. And so now if you're skeptical that any two skew lines, you can find parallel planes such that one plane contains one line and the other contains the other, well, let's just check. So it's clear that they have the same n, so they're parallel planes. These are different, so they're not the same plane. And then to, for example, confirm that L1 is on P1, you just plug in the equation for L1. So L1, this is x, y, and z. Remember, that's how the vector equation works. That R1 of t, the components of that are the x, y, and z coordinates of points on our line. So to see if this line lives on plane 1, I'll plug this x, y, and z into plane 1. So 6 times 1 plus t plus, oh, whatever, y is 1 plus 6t. So I'm going to do minus 2 times 1 plus 6t. And then z is 2t, so plus 3 times 2t. Does that equal 4 for all values of t? Well, I hope so. So this is going to be what? 6 plus 6t minus 2 minus 12t plus 6t. Does that equal 4? And yeah, what do you know? 6t plus 6t minus 12t. And so there we go. And so if you do the same thing, you can confirm that that the other line, L2, is on P2. So L2 is on P2 similarly. So if you were skeptical of our ability to find these parallel planes, guess what? We just did. And so that's proof by construction that we can do it. And so now the last thing to convince ourselves of is that the distance between these skew lines is simply going to be the distance between these parallel planes. That the closest those lines ever get to each other is going to be the same distance as how far away those planes are. So essentially that's what you do. For skew lines, you find parallel planes containing the lines, then find the distance between the parallel planes. So, and then that further reduces to distance from point to plane. So final answer would be, for example, let's do distance 0, -2, 0 to 6x minus 2y plus 3z equals -10. So I've already done that twice today, distance between a point and a plane. So I'm not going to do that a third time. But yeah, 0 minus 2, 0 is a point that is on plane 1. I didn't feel like dealing with fractions, so I just looked around and realized that, yeah, if I take x at z 0, y is -2, that works. I guess that's not your final answer, but yeah. Distance between skew lines is the distance from that point to that plane. So that's sort of the trickiest one. I don't think we would just ask you, find the distance between the skew lines. We'd probably give you a hint. I think on an exam, can't remember if it was last semester or the semester before, we put something like this on where part A was find these two planes, and then part B was what's the distance between those lines, just to get you going. But yeah, that's how that works. And so that sort of covers all the I guess I didn't do it. I'll do one more at the end, but let's do something else. Find the distance from the point 2, 3, 4 to the sphere x minus 10 squared plus y minus 9 squared plus z minus 8 squared equals 12. So later on in the course, we'll come up with some calculus techniques to approach this. I guess something that you guys maybe thought about a little bit, but haven't realized yet, is that we haven't done any calculus yet in this course. It's been 2 full weeks. You're kind of getting ripped off if this is Calc 3 and you haven't done calculus yet. But we'll do that on our first lecture next week on Monday. But anyway, we will later on have a way to do this with calculus, but for today, let's try to do this using geometry. And so this was my last tip here, that for some other kind of question, draw a sketch to try to find a hint. Okay. So point to a sphere. Okay, so I don't know, let's say I have my point 2, 3, 4 that's here. I have my sphere, let's say is over here. So x minus 10 squared plus y minus 9 squared plus z minus 8 squared equals 12. And I want to find this distance. And so what you want, maybe I'll do this in a different color. The trick here, and so this is something I don't think you want to memorize, that I think with a lot of these, you're going to want to have the picture in mind and sort of convince yourself of this. And so this is the picture you want to have in mind, that this distance that we're looking for, it's going to be this closest point on the sphere, that's the point on the sphere closest to 2, 3, 4. And so it's going to be distance 2, 3, 4 to the sphere you could figure out by doing distance to the center to 10, 9, 8 minus the radius. Well, I'll just write it like this. I'll write it distance 2, 3, 4 to center minus the radius. And I guess things would be weird if this point was inside the sphere, but you'll see that it's not. So this could get a little bit weirder. I mean, I guess technically we want to do this absolute value, but that's a weirder. We're not going to worry too much about that. So anyway, yeah, distance 2, 3, 4 to center, I guess that is a point-to-point distance formula. So that's going to be, well, what? The center is 10, 9, 8, like we said. So this is square root of, well, 8 squared plus 6 squared plus 4 squared minus, well, the radius, we look at the equation and see is square root of 12. And so, yeah, equals square root 116 minus square root of 12. If the point was inside the sphere, it would be closer to the center than the radius, and this would be a negative answer, but clearly this is a positive number, so that's what we're after. So distance to sphere is distance to center minus the radius, right? Because this blue right here is square root of 12. Okay, so that falls into the category of, yeah, just draw a picture. I mean, this perspective that I drew here, I don't know where the X, Y, and Z axes are, but it's not super important. I just have my sphere, I have my point, and this is the situation. So you don't always have to pay attention to your perspective if you're just trying to get a hint for what to try for something like this. Okay. So find the equation of the set of points whose distance to the plane x equals 2 is twice their distance to the x-axis. So we put this in this week's homework from 12.6. It turns out that some of the conic sections are characterized by different distance things. For example, an ellipse or the set of points whose, you pick 2 points which are called the foci, plural for focus. So you have your 2 foci, or I think it's foci, it might be foci, I don't know, I don't speak Latin. But anyway, you have your 2 points, and then the ellipse consists of all the points whose distance to one focus plus distance to the other focus is a constant value. A hyperbola is the same thing, except it's the difference between the distances to the 2 foci. A parabola ends up being points that are equidistant from a point and a line. I forget what those are called. I guess maybe it's a focus. I don't know. But there's different distance characterizations of some of these basic objects, and it turns out the same thing is true for some of our quadric surfaces that we talked about in 12.6. And so that's why a couple questions like this showed up on the 12.6 homework. So anyway, equation of the set of points whose distance to the plane x equals 2 is twice the distance to the x-axis. So let's see here. Got our x-axis, y, and z. I guess we have our plane x equals 2, which ends up being perpendicular to the x-axis. Okay, so what's the distance from the xyz to the point x equals 2? So I claim that it's going to be the distance to the point 2, yz. That to go directly to the left, and live on the plane x equals 2, that's the closest you're going to get. By changing y or changing z or both, you're going to be further away. So the closest you can get to the plane x equals 2 is by keeping y and z the same and doing it like that. So the distance from xyz to the plane x equals 2 is the distance I don't know how to say it, to the x equals 2 plane equals the distance from xyz to 2yz, which now you can use the point-point distance formula. You get x minus 2 squared plus y minus y squared plus z minus z squared, which is square root of x minus 2 squared, which technically is absolute value of x minus 2. Okay, and then same thing. And you could figure this out in terms of the point-to-plane distance formula from before, but for this vertical plane x equals 2, it's pretty easy to find this shadow point that's connected perpendicularly to this point. That for other planes that are diagonal, it's a lot harder to find this point here, but hopefully you're able to convince yourself that this is what we're after here. And in the same way, the distance to the x-axis from this point to the x-axis is going to be the distance from xyz to the point x, 0, 0. That to be on the x-axis, both y and z have to be 0, but if you change x, you're going to be further away. The closest point on the x-axis to xyz is x, 0, 0. So let's do that. Distance xyz to x-axis is distance xyz to x, 0, 0, which ends up, after you go through the distance formula, is going to be square root of y squared plus z squared. So find the equation of the set of points whose distance to the x equals 2 plane is twice the distance to the x-axis. We take that sentence, change it into an equation. Distance to x-axis is twice distance to x equals 2 is twice distance to x-axis, so we get that, which then you could rewrite as x minus 2 squared equals 2 y squared plus z squared, which is a cone around the x-axis. It's basically the cone x squared equals 2y squared plus 2z squared shifted 2 in the x direction. That replacing x with x minus 2 shifts it there. So I guess the drawing would be, we have x equals 2 is where the vertex is. So you have your cone around the x-axis. I guess the y-axis would be going into the page, so let's do it properly. Something like that. And then I realized just in my examples, I didn't do distance between a line and a plane. Well, if they intersect, then the distance is 0, of course. And so then the only time you'd have a non-zero answer is if they don't intersect. In which case, it's the same story that we've seen before, that these distances that we or after, you could pick any point here. So pick a point on the line, throw it out. So distance between line and plane equals the distance between any line point and plane. So that's not true if the line and the plane intersect, of course. That if they intersect, these objects have no separation. And so anyway, that's the idea. So hopefully that reinforces some of the ideas that we've been talking about. And on Monday, as promised, we'll actually get into some calculus, so you'll get your money's worth for Calc 3. But have a good weekend, and I'll see you later.